So section 1.6, the units of measurement. This little story is intended to help us understand why units are very important. In 1999, not that long ago, NASA lost the $125 million Mars Climate Orbiter. They sent it up to Mars. It was supposed to orbit and take all kinds of cool measurements and stuff. It orbited too low, got into the atmosphere, got sucked in by the gravitational force of Mars, and burned up. So, of course, there was an investigation, and the conclusion was the root cause of the loss of the spacecraft was a failed translation of English units into metric units. One group of engineers was using centimeters, one was using inches. They failed to communicate. $125 million, plus who knows how many people's time, right, wasted because of a miscommunication about units. So I'm going to be on top of you about units in this class, and that's because units are really, really important. The units that we use, and units are just standard quantities that specify measurements, are really, really important. There's two basic systems of units. The metric system, which most of the world uses, and the English system that we hold on to for dear life here in the United States. The English system is not a great system. Okay? The metric system is far better. What scientists use is actually called the International System of Units. The abbreviation is SI from the French. I'm not good at French pronunciation, so I'm not going to say that. That's why the I comes after the S. The SI system is based on the metric system. The differences are very subtle, and for the purposes of this class, they really don't matter at all. But I just need to tell you that. Okay, so here are the SI base units. Some of these we will encounter, some of these we will not. So we're going to end up using these: length, mass, time, temperature, and amount of substance. The base units, meters, kilograms, seconds, Kelvin, and mole. Really the only difference here with the metric system is the base unit in the metric system for mass is the gram, not the kilogram. Big deal. I'm not going to quiz you on what is the base unit. I'm going to want you to learn how to use the units. Okay? And here are their symbols. One thing that's a little different with the metric system or the SI system is unit abbreviations do not have periods. So when we abbreviate inches as IN, we put a period after it. Metric abbreviations do not have periods. Okay? So what are these different quantities? The meter is used to measure length. Okay? And I want you to have a grasp for how big a meter is. Okay? Now, of course, today, oh, there it is. It was too close to me. I couldn't see it. A meter is a little bit longer than a yard. Okay, this looks like a yardstick, right? It's actually a meter stick. It's a little bit longer than a yard. If we look, it does have inches marked on one side. It's actually a little over 39 inches long. A yard is 36 inches. But in terms of ballpark sizes, meters and yards are about the same size. All of these units are defined very precisely. Not going to quiz you on these either, but I do list them here on the slides if you're interested. Mass. Mass is similar to weight, but not the same. It's a measure of how much matter is in the object. So the SI unit is the kilogram, abbreviated kg. A kilogram is just over 2 pounds. Okay? So a kilogram is about 2 pounds. You should know that. The unit we use more commonly in chemistry is the gram. A gram is 1/1000th of a kilogram. To give an idea of how big a gram is, a nickel, 5 cents, weighs approximately 5 grams. So a gram is a small unit. The difference between weight and mass is that weight is a measure of the gravitational pull on an object. It's It's actually a unit of force. And mass is the quantity of matter. So the quantity of matter in a substance does not change whether you're on Earth or in outer space or on Mars. But the weight of an object will change. In outer space where there's no gravity, everything is weightless. Does that mean it doesn't have any molecules or atoms in it? No, the amount of matter is the same. Time. Okay, we're all familiar with time, and we're familiar with the unit second. And happy for us, the second is the same in all of the different time systems of units. So the SI unit of time is a second. And it's defined very precisely in terms of radiation events in cesium-133. For temperature, and we'll talk more about the different temperature scales, but the SI unit is the Kelvin. We talked a little bit about energy and thermal energy. Temperature is a measure of the average kinetic energy that the particles in a substance have. So we talked about students and wiggling, right? Yesterday I actually got the class they wouldn't like jiggle around and be crazy, but I got them to wave their hands at me. So everybody waving their hand at me, can you guys do that? Wave at me. Say hi. Okay, see, increased kinetic energy, increased movement, the temperature went up. That's what happens with molecules. So temperature is the average kinetic energy. It's measured in kelvins. Temperature also determines how thermal energy will transfer. Thermal energy always moves from the warmer object to the cooler object. So here are the temperature scales. In the United States, we tend to use the Fahrenheit scale. And, in my car, I was driving home yesterday, it was 53 degrees Fahrenheit. The metric system uses the Celsius degree. It's also sometimes called the centigrade scale. And that bases 0 on the temperature at which water freezes, and it bases 100 degrees on the temperature at which water boils. The Fahrenheit scale was based on some practical things when it was created, but it's not all that useful anymore. So in science, we always use the Celsius or the Kelvin scale. The difference between Celsius and Kelvin is that Kelvin bases 0 not at the freezing point of water, but at the absolutely lowest temperature that could ever be achieved, absolute 0. Temperature is a measure of the kinetic energy of an object. So if the absolute temperature is 0, what that means is the particles in it have 0 kinetic energy. They are not moving at all. And scientists have actually gotten extremely close to 0 Kelvin, but nobody's actually gotten all the molecules to just be still like that. The nice thing about the Kelvin scale is there are no negative temperatures. And we'll be using that scale when we talk about gases. So we need to be able to convert between these 3 temperature scales. So between Celsius and Fahrenheit, the conversion is a bit complicated because 0 is in a different place and the degrees are different sizes. And so the easiest thing to do is just to use algebra and to use this formula. The Celsius temperature is going to equal the Fahrenheit temperature minus 32 divided by 1.8. So that's the equation that helps us to convert between Celsius and Fahrenheit. Between Celsius and Kelvin, it's just an offset in where 0 is. Let's look back at these thermometers here. So here's 0, and over here, that corresponds to 273. It's actually 273.15. If we go up 100 degrees Celsius, we get to 100. If we go up 100 kelvins, we get to 373. The Kelvin unit is the same size as the Celsius degree. It's just that 0's in a different place. So then the conversion is that the Kelvin temperature equals the Celsius temperature plus 273.15. You should all have learned how to do these calculations previously. So let's just do an example. Gallium, that's a fun metal. Gallium is a solid metal at room temperature, but it will melt to a liquid in your hand. It's a metal that melts in your hand. I mean, M&Ms don't even melt in your hand, right? But it'll melt at body temperature, the temperature of your hand. So the melting temperature of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? So they're asking us two different things. We're going to talk a lot more about problem solving in this lecture, but this one shouldn't pose too much trouble. So for A, we're trying to convert from degrees Fahrenheit to degrees Celsius. When we're doing temperature conversions, we need the equation. So degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. So we need to take our Fahrenheit temperature, plug it into this formula. So I'm going to put 85.6 in here. I'm going to subtract 32 and divide by 1.8. It's important to communicate with your calculator correctly. You want your calculator to finish that subtraction before it divides by 1.8. You can do that either by using parentheses or by pressing equals at the correct time. So I'm going to be doing this on my TI-36X Pro. If you have your calculator with you, you should be sure to bring it out and do these with me. Make sure that your calculator is understanding how to do these problems. So I'm going to take 85.6 minus 32. I'm not a fan of parentheses. So I'm going to press equals to tell my calculator, finish the subtraction. My calculator is now showing me 53.6, and then I'm going to say divide by 1.8 and press equals again. The number my calculator shows me is 29.77, and it just goes on and on until the display runs out. 77 repeating, and that would be degrees Celsius. We'll talk about significant figures. You should all at least remember trying to learn significant figures, so it's not a completely strange concept to you. There's a shortcut with temperatures. So here, the starting temperature had 1 decimal point, so that means we should round our converted temperature to the same decimal place. So I'm going to write this answer as 29.8 degrees Celsius. Okay, so that's the melting point of gallium on the Celsius scale. Any questions? So the next part, and when there's multiple parts to a question, it's really, really important to answer both of them. What's that temperature on the Kelvin scale? Well, we could take Fahrenheit and go to Kelvin, or we could take this Celsius and go to Kelvin. Did we have an equation between Fahrenheit and Kelvin? No, there wasn't one given. It's not really very useful. So we actually need to start with this Celsius temperature. So what I'm going to do is I'm going to start with the unrounded Celsius temperature. So I'm converting here. I'm going to go from Celsius to Kelvin. I need an equation. Kelvin temperature equals the Celsius temperature plus 273.15. So I'm going to plug in my number, 29.77 repeating, plus 273.15. So I still have that 29.7777777778 in my calculator. I'm just going to add 273.15 equals, and my calculator is showing me 302.9277, again with the repeating business. The unit there is capital K for Kelvin. The unit is Kelvin. It's not a degree Kelvin. To round this number, I'm going to look back at the original number. Not this 29.77, but where I actually started from with the Fahrenheit. That had 1 decimal place. I'm going to round this one to 1 decimal place. And so I'm going to express this answer as 302.9 Kelvin. If you are curious why I'm doing that shortcut with sig figs, ask me during lab. I just don't want to take lecture time for it. Any questions? Yes?
Yeah, would you have to memorize the equations?
You should memorize those equations, yeah. Yep. We're going to use them a lot. Any other questions? Okay, so the metric system. Using the metric system and also just other calculations in chemistry, we are going to be using scientific notation. You should have learned scientific notation in your previous chemistry class. If you're rusty on it, Appendix 1A in your textbook has a review of that. I'm not going to cover it in lecture. You're welcome to ask me about it outside of lecture, but I'm going to assume that we're all okay with scientific notation. So, the SI system and the metric system use prefix multipliers. And what those multipliers do is they make the units bigger or smaller. The reason we want to do that is because it's convenient to have a unit that is similar in size to what we're measuring. Okay, so I live in Reedley. We are in Fresno. So the distance is it's like 27, 28 miles, something like that. We measure a distance like that in miles. If I told you what that distance was in inches, that would be kind of ridiculous, wouldn't it? And the number would be so large that it wouldn't really mean much, okay? But if I want to know how long my stylus is, and I'm just being a typical American, I would probably measure that in inches and not in miles, right? So we like to use a unit that is similar in size. That's why we have inches and feet and yards and miles and leagues and light years and all those different lengths. In the metric system, we just use prefixes, and the prefixes change the size by factors of 10. And the prefixes are the same whether you're applying it to grams or to liters or to seconds or to anything else. So in the English system, there's 12 inches in a foot, and there's 3 feet in a yard. I can't remember the yards to miles, but it's 5,280 feet in a mile. All these crazy numbers to remember. The beauty of the metric system is it's a list of metric prefixes. They are all factors of 10. You learn those, you're great. You can do any conversion in the metric system. So, like, for example, kilometer. This prefix kilo stands for 1,000 or 10 to the third. These are just different ways of expressing the same value. So 1 kilometer is 1,000 meters or 10 to the third meters. So a kilometer is bigger than a meter by a factor of 1,000. So these are the prefix multipliers that your book gives you. And most, if not all of these, are on the list of things I'm telling you to memorize for the quiz next week. So you should memorize the prefix name. Spelling is kind of important. You should memorize the symbol, and you should remember the multiplier. I don't think these decimal expressions of the multiplier are very useful. I think the 10 to the something is a lot more useful, and that's what I'll always be using in class. So here we've talked about kilo. The abbreviation is a lowercase k. It means 1,000. It means 10 to the third. So some of these are a lot more common than others. We're going to use kilo and centi and milli and micro. Those are probably the most common ones that we'll use in chemistry, but you need to know the rest of them too because they'll show up in problems. The M's can be a little confusing. There's mega and milli and micro. So we've got capital M for mega. Mega makes things bigger. So mega multiplies that unit by 1,000,000. Milli multiplies it by 10 to the minus third, or divides by 1,000, makes it smaller. So milli has the abbreviation lowercase m, small m. Big M, bigger unit, small m, smaller unit. We ran out of English m's, so then we went to the Greek, and we're using the Greek letter m, which is the mu, and that means 10 to the minus 6, or divided by 1,000,000. Okay. So how long is 4.5 megameters in meters? Now these questions are not get out your calculator kinds of questions. These are just, what does that prefix mean? Well, the prefix capital M is for mega, and that means 10 to the 6. Okay? So if I write 4.5 megameters, you need to make sure that mega m is definitely larger than your lowercase m for the meter. Otherwise, it's going to look like millimeters. Then over here, what I can do is I can say, well, that's 4.5. Now, instead of capital M, which is like an abbreviation, I'm going to write what it means. It means 1,000,000, or 10 to the 6. So that's 4.5 times 10 to the 6 meters. And that's how you make a conversion factor with metric units. On one side of the equal sign, you write it with the prefix, and on the other side, you write it with what the prefix means. Any questions? You should have learned this before, but my experience is a lot of students are still a little bit shaky on this. 7.13 times 10 to the minus 9 liters. How many nanoliters is that? Well, what does this prefix nano stand for? Nano is lowercase n. Anybody? 10 to the negative 9. I remember that one because nano and nino, nano 9, negative 9, that remind me of each other. So nano means 10 to the minus 9. Look, this is times 10 to the minus 9. To convert that to nanometers, I'm just going to write nano instead of 10 to the minus 9. Now, all of your conversions are not going to be that simple, but these are just to help us understand what the heck is it that we're doing with these silly numbers and letters. Any questions? So we talked about basic units. We also need to talk about derived units. These are combinations of other units. Things like miles per hour, meter per second. So meters per second. Meter is a unit of length, and second is a unit of time. So this is measuring a speed or a rate. One that we use a lot in chemistry is volume. Volume is a measure of an amount of space. So this can be measured using a length unit cubed. So any length unit, when cubed, becomes a unit volume. So examples are cubic meters, cubic millimeters, cubic centimeters. Other common volume units are the liter and the milliliter. And so in English units, this would be like, cubic inches or cubic yards. And this would be like gallons and ounces, fluid measures, right? So if we look at this cube here, it's 10 centimeters on a side. It has 10 little boxes on each side. And we should remember from geometry that the volume of a rectangular solid is equal to the length of it times the width times the height. This is a cube, and so it's the same in all dimensions. So the volume of this is equal to the length, which is 10 centimeters, times the width, which is 10 centimeters, times the height, which is 10 centimeters. Well, if you do the math there, 10 times 10 times 10 is 1,000. And the units, centimeter times centimeter times centimeter, that's centimeters cubed. This is also equivalent to 10 cubed cubic centimeters. So that's how a length unit can be used to measure a volume. This large cube has 1,000 little 1 centimeter cubes in it. Any questions? Should go back here for a minute. This little cube here, its volume is 1 cubic centimeter. That volume has also been assigned the name milliliter. So 1 cubic centimeter is equal to 1 milliliter. This is a very simple relationship, but it's one that students forget about. And so you'll be doing unit conversion problems and you get stumped. Don't forget, a cubic centimeter is the same as a milliliter. So here are some common units and their equivalents. For the most part, you do not need to memorize things like this. We need to memorize the metric prefixes and know how to use those, but converting between the English and metric system, most of the time on, say, an exam, I will give you the needed conversion factors. There's one exception. I want you to memorize this one, the one between inches and centimeters. 1 inch equals 2.54 centimeters. We use that one a lot. It's important. So you should memorize that one and you should memorize this one. Cubic centimeter equals a milliliter. Another derived unit is density. So the density of a substance is a ratio of mass to volume. The mass of the object divided by the volume of an object. So we can say density equals mass divided by volume, or just using letters, D equals M over V. And that's an equation that you should memorize if you don't already know it. So common units of density for liquids and solids are grams per milliliter, grams per cubic centimeter. For gases, we tend to use grams per liter. Density is a physical property. We talked about physical and chemical properties. It's a physical property of a substance. It does depend on the temperature of the substance. So it can vary a little bit with temperature. Here's a table of some common substances and their density at 20 degrees Celsius. And so when you're doing homework and you need to use a density, they may not give it to you. They'll make you go look it up. You do not need to memorize densities. The only one I'd like you to remember is the density of water. Wait, that's not water. Missed it a little bit. The density of water. This is technically at 4 degrees, but there are many times where we're doing really more of a rough calculation, and so the density of water is 1 gram per milliliter. That's not a coincidence. Actually, the grams and milliliters, the sizes were determined so that water has a maximum density of 1. So we see here that some things are less dense than water and some things are more dense than water. Gold and platinum down here are very, very heavy for their size. So density, this density is kind of related to that old joke, which weighs more, a pound of feathers or a pound of bricks? They weigh the same. They each weigh a pound. Which one takes up more space? The feathers. The feathers are much less dense. A pound of feathers is going to look a lot larger than a pound of bricks. They weigh the same though. So density is how heavy something is for its size. If you take a piece of, let's say, gold, density 19.3 grams per cubic centimeter, and you cut the piece of gold in half, and you put one aside and you're just looking at half of that piece. Have you changed the mass of the piece of gold? Yeah. Have you changed the volume? Yes. You cut both of them in half. The density remains the same. So the density of something is the same at a given temperature, regardless of whether you have a whole bunch of it or just a little bit of it. Sometimes students will tell me, well, that one's going to sink because it's a bigger piece. Well, no, it isn't. The smaller piece is going to sink too. It's the density, it's not the mass of the object that determines whether something's going to sink in water. That brings us to intensive and extensive properties. So an intensive property does not depend on how much of the substance you have. So density is an intensive property. The intensive properties have to do with the nature of that substance. They are intrinsic. Doesn't matter how big the piece is. So the melting point, the color, here I've got a purple sweater. So if I cut the sleeve off of my sweater, is it still going to be purple? Yeah. Will the mass of the sweater change? Sure. Will the value of the sweater change? Yeah. The color's not going to change. The color doesn't depend on how big the sweater is, right? The density doesn't depend on how large the object is. The density is an intrinsic and intensive property. Extensive properties just lost all my words. Extensive properties do depend on how much stuff there is. So it's more of an external thing. The mass of something, I take a piece of wood, I cut it in half. The mass changes. The color doesn't change, the density doesn't change. Those are intensive properties. But the mass changes. The volume changes. Okay? So those are extensive properties. Any questions? Okay, let's calculate density. We have a lot of, we call them story problems when I was growing up. I think they call them word problems now. Story sounds friendlier to me, but there's a lot of word problems in chemistry because word problems is how math gets applied to real life, and so they're unavoidable. And I know some of you probably don't like word problems, but you can learn how to deal with them, and I will help you. So many times, there's a lot of extra words in the problem. That's the story. So this one has quite a story. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. This has all sorts of implications for their relationship, right? So he places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? Well, density is an intensive property. If this ring is made of platinum, its density should be the same as the density of platinum, which we can look up in this handy-dandy table of densities. Density of platinum is 21.4 grams per cubic centimeter. And there's our density equation. So density equals the mass divided by the volume, and the density of platinum is 21.4 grams per cubic centimeter. So we need the mass of the ring and the volume of the ring. Well, he put it on a balance, and he found that it was 3.15 grams. So we're going to plug that in here, 3.15 grams. And the volume. Well, a ring isn't like a little cube that you can measure with a ruler. It's an unusual, you could calculate the volume of a ring, but it'd be tricky. An easier way is to take a graduated cylinder with water, measure how much water is in there, put the ring in, when you put something into water, the water level rises, right? We all have personal experience with that. You don't want to fill the bathtub too full, because when you get in, a whole bunch is going to slosh over, and whoever's in charge of the house is going to be angry. It might be you. You still don't want to have that happen. So that's how he measured this, 0.233. It displaced that amount of water. The amount of water that got displaced is equal to the volume. So we're going to put that in here, 0.233 cubic centimeters. And then we're going to use the calculator, 3.15 divided by 0.233. Another good reason to always do these calculations on your calculator is because I make mistakes. I'd like to say that I make them on purpose, just to test you, but the truth is I just screw up. And it's awfully fun to catch the instructor making a mistake in a video that'll be on YouTube later. So fun. Okay, so anybody else get that, 13.5? So is this ring made out of platinum? Nope. The density's wrong. It may look like platinum, but it's not. If we go back here, 13.5, well, 13.5 is the density of mercury. It couldn't be made out of mercury, though, because mercury is a liquid at room temperature. How would it be possible to have a metal with a density of 13.5? A mixture. It might have some platinum in it. Where's my pointer? Some platinum. The rest of it could be lead or aluminum or something. That would make the density lower if you mix those two things together. So this guy's ring is not platinum. So here's the second one. The woman in this example is shocked that the ring is fake. She was not trying to be cheap. She got cheated. So she buys a new ring. This one has a mass of 4.53 grams, a volume of 0.212 cubic centimeters. Is this one platinum? Well, we just did this calculation, so we should be able to do this fairly quickly now. Density equals mass divided by volume, right? So we've got the mass there, 4.53, and we've got the volume, 0.212 cubic centimeters. 4.53 divided by 0.212. So this one comes out 21.4. So what do you think? Is this one platinum? Yeah. 21.4 is not exactly the same as 21.5. But measurements were made, and there's always a little bit of error in measurements. So that is close enough to say, yeah, this time she got the real thing. Any questions? Yes? We are going to cover how to round it in a few minutes. Good question. Any other questions?